Okay, so this is the first video for the section 3.9 for differentials. And differentials, I guess, is our last application of derivatives, and it really focuses on change, like and really approximating that change using the derivative. And the reason this can work is if you're near a tangent line, and remember a tangent line, we're thinking about, okay, that's just like if we're looking at the derivative, the slope of that tangent, like if you're near that point of tangency, the function and the actual line I mean, they're very, very close to each other. You know, and in fact, like if you were to zoom in and focus just like on that point of tangency, right? The closer you got to that point of tangency, the less of a difference you would notice between the actual function itself and the graph of the line, right, of this tangent line. And so sometimes functions might be too complicated or too hard, or maybe we wouldn't even know what those functions are. But we can look at the tangent line or get a linear approximation of that function, and sometimes that approximation is good enough. And that's sort of where linear approximations or differentials, and I'm going to use them both, come into play. Because you're really close to that point of tangency, and sometimes close enough is a good enough approximation. Okay, so let's look here first, just in terms of, okay, you know, it gives us the word and the phrase linear approximation, right? So we're going to use the linear approximation, or we're going to use the tangent line as opposed to the function to evaluate f of 1.02. And it seems sort of, I think, unreasonable. I think it's very unreasonable to actually do 1.02 cubed squared, right? I mean, like, we're not testing arithmetic, we're trying to, you know, learn calculus. So, but 1.02 is really close to 1, and so I might want to find the equation of the tangent line at 1, because x equals 1, like I know what's happening at 1, and then at least it's an easier value to calculate, and then use the linear approximation at 1. Oh yeah, I even said it right there. Should read my own problem. To evaluate 1.02. Okay, so to get the linear approximation, first you need is a slope. So we find the derivative, which is 6x squared minus 8x, and then we evaluate 1. So what's the derivative at 1? So that would be 6 times 1 minus 8 times 1, or negative 2. And a linear approximation, you need a line, so the equation of the line would be y minus y1 equals m times x minus x1. We know the slope is negative 2. We know our x value is 1. And then, so if we put in 1 into the actual function itself to get the corresponding y value, 1 cubed is 1, so we have 2 times 1 is 2. Minus 4 plus 1. So it's negative 2 plus 1, which is negative 1. So the point is 1 comma negative 1. That's what we're interested in. That's our point of tangency. So then since the y-coordinate is negative 1, we make it that. So here is our equation of the tangent line. So that tangent line and this curve are going to be really, really close to each other at the point of tangency, at x equals 1. And then the farther you move from that, obviously the more different the function values will be. So I can use this to evaluate 1.02. So then I could say, okay, so I would say maybe like, okay, y plus 1 is equal to negative 2 times 1.02 minus 1. And so then I could say, okay, so y plus 1 equals, well, that's 0.02 times negative 2 is negative 0.04. And then subtract 1, so y equals negative 1.04. Now this isn't the exact answer, but it's an approximation. It's pretty close to that exact answer. And you know, if you put out your calculator and actually evaluated 1.02 in this function, you can see just how close your approximation was. Okay, now that's using the linear approximation. That's actually using the tangent line. And again, this line came from finding the slope through the derivative at this point of tangency. Notice that if I wanted to evaluate a different point, let's say like 3.5, this is a terrible approximation because 3.5 is nowhere near 1. So you would choose a different point to find that linear approximation. Now, oh, a timer, how nice, not sure why. Go away, timer. Anyway, so sometimes all you want to know is just the change, right? And so that's where this idea of a differential comes into play. Because differential, you're just interested in, well, how much did y change by? How much did y vary by? And so, like again, you read through this, it tells you how much you deviated from the true value. So it's not necessarily interested in what is the true value, but how far are you from it? And that's a differential. And how far you're from the y variable will depend on like how far you deviated from the x. And so there is a formula, but it's nothing fancy at all. I mean, I'm saying, oh, the amount y deviates is equal to the slope of the tangent line times the amount x deviates. But in all honesty, all I did was took dy dx, which is equivalent to the derivative of some point, and you can just multiply your dx to the other side, right? So that's how you get dy, the amount y deviates is equal to the derivative times the amount x deviates. So it's nice to know this structure, and I'll start off with the structure when it asks us to find differentials, but it's not, like I said, it's just the derivative multiplied across, okay? So look at example 1b, exact same problem, but now it says use differentials. So when you see the word differentials, you want to know, if you just want to focus on how much the y deviates. So you would say, okay, dy, the amount y deviates, is approximately equal to the derivative at the point times how much x deviated by. So the derivative at the point, so you have to sort of interpret this. It doesn't directly say or explicitly say that we're looking at 1, but it seems to make sense that 1 would be our value because that's like 1.02 is really close to 1. So the amount y deviates could be approximately calculated by the derivative at 1 times how much did we deviate from 1. We deviated from 1 by 0.02. And I think I can use dx as a notation. Sometimes I might use like a delta x, that's fine too. Okay, so now I need to find the derivative at 1. And like I know I already solved it, but in case you want to say, okay, well, how would have I done this had I not solved a? I'd say, okay, the derivative expression is 6x squared minus 8x. So the derivative at 1 is negative 2, right? Because 1 squared is 1 times 6 minus 8. So then I'd say, okay, the derivative is negative 2 times 0.02. So then I would get the amount that y deviates is approximately equal to negative 0.04, which we had in the last example. But this focuses just on the change. So if you knew what you should have gotten, this is how much you add to that true value or to the tangent value. So again, if you actually estimated, if you actually put in 1 to this function and found, okay, what is f of 1? Okay, so the value of f of 1, and we did this before, should be negative 1. 1 cubed is 1 times 2 is 2. 2 minus 4 is negative 2, plus 1 is negative 1. So if you know f of 1 is negative 1, and we're deviating by 0.02 from that value, then we're going to deviate in the y direction by negative 0.04. So then I could say, okay, so f of 1.02 approximately equals negative 1 plus this change of negative 0.04 and negative 1.04. So again, another way to solve the exact same problem, but it just focuses on the difference. That's the differential. Okay, so let me do another video and we'll do the next couple of examples.